So within this this whole setup, we're actually gonna, there's a few different ways, even once you have this hardware setup, that you can try to do this. But we're going to use what's called the Barret-Kok protocol. The Barret-Kok protocol is what's called a two-round protocol, a two-click protocol, and it's useful because it's robust against photon loss. So, and as I said, because we have fibers here on which our photon states can get lost, it's important to be able to know when that happens. So if you don't do this, you can sometimes think that you've had a successful entanglement swap, even if you haven't. The Barret-Kok protocol can still get fooled by things like dark counts, but from photon loss itself, it will always be able to tell you that you have failed your swap. So increasing fiber length and increasing loss will increase the time that it takes to get a successful swap happening, but you'll always know that you'll never think that you got a success when you didn't. So this round is, I'm just gonna kind of go through it at a high level, but this has two rounds. In the first round, we do what I mentioned before, where the memories entangle their two qubits and then send one qubit along as a photon. These then go and get measured by the swapping station, who then sends a result back to Alice and Bob. And so based on this result, they either failed or they succeeded. If they succeeded, they move on to round two. They apply an operation onto their memory qubit, entangle and emit again, and then again wait for a response from the swapping station. And if successful, they have to apply a small final correction onto their qubits, and then they are done. They have entanglement. But note that even with perfect parameters and no loss, the total success probability here is 50% at max. So here we have a little script that does the Barret-Kok protocol in this kind of setup. We're going to be going for 10 kilometers per fiber in this case, and you can see our frequency parameters here. But basically, and we have a lot of logic that sort of does the Barret-Kok protocol as I just described. But what I wanted to show you is setting up the network itself. So here we have our memories that are going to be going into Alice and Bob, and here we just set some delay values for how long operations take. It's not a big deal, but we can set, of course, a lot more parameters of these memories. But here we're just kind of assuming that they're fairly perfect. And we also have our transducers, which you have specified what frequency and bandwidth and polarization that they have put in. And then we go ahead and connect our memories to our transducers. We put the whole thing into nodes and put those nodes into a network. And then we connect that network by using what's called a BSD fiber link. It's just a beam splitter detector fiber link, and so contains all of the stuff in this part outside of the nodes itself. So within that is a fiber and the beam splitter detector, as we already saw. Okay, and then they're each equipped with this Barret-Kok protocol, and we can run this example and see what happens. Takes a second to import. Okay, so we just saw a lot happen there. So each of these is a run that it has tried to generate entanglement with, and we have a bunch of outputs here that we just have in our protocol. Like when our protocol does something, you say output in an info line that it did this. You can specify in your simulation what you want output or what you don't. But in this case, we see that it took 4 tries. It took 4 tries before they were able to both get round 1 and round 2 successfully. And in the end, because we have everything here is perfect, they get a perfect Bell state at the end. And you can see that the fidelity is 1 here. And so from this, we can know what fidelity is that we get, how long a given attempt it takes, as well as how many attempts you need on average to do it. And so if you do this again, right, the number of attempts may be different because it's stochastic in the end. So in order to get a good model of the statistics of how long this will take, you will want to run several cases. So here we have just 2 runs. Other times might be more.